Hi, future doctors. Imagine you are at a Diwali Mela, surrounded by the tempting aroma of jalebis and the sweet symphony of festive music. You grab a piping hot jalebi, and as that sugary goodness hits your tongue, a surge of energy courses through you. That, my friends, is the magic of glucose in action. And today we are diving deep into the very first step of how your body turns that jalebi into fuel: glycolysis. Consider this: a young boy arrives at a clinic in rural Bihar, weak and listless. He's been suffering from diarrhea for days, unable to keep down any food. His blood sugar is dangerously low. Why? Because his body, starved of glucose, can't perform glycolysis, the fundamental pathway that provides the energy he needs to even lift his head. This, my friends, underscores the critical importance of understanding glycolysis, not just for exams, but for diagnosing and managing patients right here. Now, glycolysis literally means sugar splitting. It is the 10-step biochemical pathway that converts glucose, which is a 6-carbon sugar, into two molecules of pyruvate, which is a 3-carbon molecule. It's the first stage of cellular respiration. And it's a universal process which is present across all living organisms, from the smallest bacteria to the largest whale. It's the cornerstone of energy production, particularly crucial in resource limited settings like hypoxic tissues or in conditions like that boy's hypoglycemia. Our understanding of glycolysis has a rich history, starting with Louis Pasteur's work on fermentation in the 19th century. Later, Edward Buchner's discovery of cell-free fermentation paved the way for understanding the enzymatic nature of glycolysis. The detailed pathway as we know it today was elucidated through the combined efforts of brilliant minds like Emden, Meyerhoff, and Parnas, giving rise to the alternative name Emden-Meyerhoff-Parnas pathway, or in short we call it EMP pathway. Now coming to the key concepts. Now when we talk about the key concepts, we are going to talk about the steps and energetics of this pathway. Glycolysis takes place in the cytoplasm of the cell and can be divided into two main phases. The first is the energy investment phase and the energy payoff phase, the second. Now think of it like investing in a successful IPL team. You spend some money upfront to build a strong squad, but the returns in the later stages are much higher. So starting with the investment phase, right? The first phase. Step 1. That is the phosphorylation of glucose. Just like adding a reserved sticker to a seat on a crowded Mumbai local train, hexokinase uses ATP to phosphorylate glucose, forming glucose 6-phosphate. Now, this traps glucose inside the cells and prevents it from leaking back out. This step is irreversible and regulated. Imagine the chaos if anyone could just hop on and off the train at any point, right? That's why we are trapping the glucose inside in a way. The step 2 is isomerization. Phosphoglucose isomerase rearranges glucose 6-phosphate into its isomer, which is fructose 6-phosphate, preparing the molecule for the next crucial phosphorylation. Think of this like changing the formation of your cricket team to maximize its potential. Then comes step 3. Phosphorylation of fructose 6-phosphate. This is the committed step of glycolysis, catalyzed by the crucial regulatory enzyme PFK1 or phosphofructokinase 1. Another ATP molecule is invested, and phosphorylation of fructose 6 phosphate to fructose 1,6 bisphosphate occurs. So another phosphate is added to this compound. This is like buying the best batsman for your IPL team. A significant investment, but crucial for future success, right? Because energy is being used. Next step is the cleavage. Cleavage is done by the aldolase enzyme. It cleaves it into 3 carbon molecules, which is glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. Imagine splitting your cricket team into smaller, equally powerful units. Then step 5, which is isomerization. Now, triose phosphate isomerase rapidly interconverts dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. This ensures that both products of step 4 can proceed through the pathway. Think of this as ensuring both your smaller cricket teams have an equal chance to win. Now, this was just the phase 1. The phase 2 begins now, which is the payoff phase. This is where the energy is actually received, right, after the investment. So this brings us to the step 6, oxidation and phosphorylation. Glyceraldehyde 3-phosphate dehydrogenase GAPDH oxidizes G3P, glyceraldehyde 3-phosphate, generating NADH, a high energy electron carrier, and adding an inorganic phosphate, forming 1,3-bisphosphoglycerate. This is like your star batsman hitting a 6, generating a burst of energy. Then comes step 7, substrate level phosphorylation. Phosphoglycerate kinase transfers a phosphate from 1,3-bisphosphoglycerate to ADP, producing ATP and 3-phosphoglycerate. This is our first ATP payoff, like winning the first match of the IPL season, right? We wanted the payoff. Then comes step 8, isomerization. Phosphoglycerate mutase rearranges 3-phosphoglycerate to 2-phosphoglycerate, setting the stage for the next high energy phosphate transfer. Then comes dehydration. Enolase removes a water molecule from 2-phosphoglycerate, creating phosphoenol pyruvate. Dehydration. Enolase removes a water molecule from 2-phosphoglycerate, creating phosphoenol pyruvate, which is a high energy compound. Think of this as concentrating the energy, like focusing your team's effort for the final match. Finally, the step 10 is substrate level phosphorylation once again, where pyruvate kinase transfers the phosphate from PEP, phosphoenol pyruvate, to ADP, generating another ATP and pyruvate, the final product of glycolysis. This is like winning the IPL trophy, a significant energy payoff. Now we come to the net energetics. The net energetics are pretty simple here. 2 ATP were invested and 4 ATP were produced. So net gain will be 2 ATP, which is 4 minus 2, 2 NADH and 2 pyruvate. Now coming to a bit of the clinical and physiological connections, and imagine glycolysis is vital for various physiological processes, right? Red blood cells lacking mitochondria rely entirely on glycolysis for ATP because it occurs in the cytoplasm, right? During intense exercise, when oxygen supply to muscles is limited, anaerobic glycolysis provides a rapid but less efficient energy source. This explains the muscle burn you feel after a strenuous workout for a long, arduous trek in the Himalayas. Certain enzyme deficiencies in glycolysis, particularly pyruvate kinase deficiency, can lead to something called hemolytic anemia, right? The breakdown of RBCs in a way. This condition more prevalent in certain parts of India due to consanguineous marriages results in fragile red blood cells that break down easily, and it leads to, of course, anemia and jaundice. Then there's something called lactic acidosis. In conditions like sepsis or severe dehydrations, tissues may experience oxygen deprivation. Now, this leads to increased reliance on anaerobic glycolysis. This results in excessive lactate production because of that last step, causing lactic acidosis, a potentially life-threatening condition often encountered in emergency rooms. Now, let's make remembering the steps of glycolysis easier with a food mnemonic, okay? So, good food promotes perfect health during intense exercise, preventing problems. Okay, so each word represents the first letter of the substrate in each step. Glucose, fructose 6-phosphate, fructose 1,6 bisphosphate, and so on. Okay, so good food promotes perfect health during intense exercise, preventing problems. So we have journeyed through the fascinating world of glycolysis, the sweet symphony of energy production. Remember, glycolysis converts glucose to pyruvate, generating 2 ATP, 2 NADH, and 2 pyruvate molecules. It's regulated at key steps by enzymes like hexokinase, PFK1, and pyruvate kinase. Dysfunction in glycolysis can lead to conditions like hemolytic anemia and lactic acidosis.